Okay, so let's first understand this adiabaticness or the adiabatic evolution in classical mechanics. And let's look what it implies in classical mechanics, and then we will extend those results in quantum mechanics. Clear? So let's write. Okay, so let's consider the harmonic oscillator. Okay, which is having a time-dependent frequency. Okay, so let me consider a harmonic. Okay, so we'll first consider it in the classical mechanics. So then we'll understand what exactly this approximation means. Okay. So consider the harmonic oscillator. With time dependent frequency. So what I mean by that, so you are having this h, x, t, and it's also the function of now the omega will be explicitly dependent on time. Okay, so I will write it as like this in p square by 2m plus half of m omega square. So this is the function of time. Clear? So you have this kind of equation now. So you can write now this dh by dt. So let's review these equations of motion. Okay, so now look here. So if this is time independent, then p and x does not depend on time. Clear? So they are independent variables in the problem. Now you are having this omega dependent on what? Time. So there may arise an explicit time dependence in both x as well as p when you calculate the equation of motion. Clear? Okay, so let's write this dh by dt. So it will be simply partial h by partial x, because it is a function of this position, and then x dot plus partial h by partial t, then p dot plus partial h by partial t. There is no t dot. Okay, so it is partial t by partial t. That's one. Clear? Okay, so you have the Hamilton's equations of motion. Okay, so what are those? So equations of motion you write as x dot as partial h by partial t, and p dot as minus partial h by partial x. Clear? So let's substitute them here. So when you write x dot here, so this term will cancel out with this term. Okay, so this implies therefore dh by dt that is same as partial h by. Clear? So now if the Hamiltonian does not contain explicit time dependence, so this term will be 0 and you are having the conserved energy. Clear? Got it? Okay, so we have not yet asked how fast this omega varies with time. Okay, so that we are going to explore. So now let's calculate this dh by dt. Okay, so that means I need to what? Partial h by partial t. So this is a very important relation. So I have to only, while you are having the explicit time dependence, that is this very term. Clear? So what will be that? So it is simply m omega and omega dot. Clear? And x square. So is this the case? Okay. Okay. So now let's write the. Okay. So let's try to vary. So I should put this. This is a function of time. So let's try to understand what this adiabatic evolution means. Clear? Okay, so this harmonic oscillator, let's call the time period of this harmonic oscillator t. So it will be how much? 2 pi by omega t. Clear? So this is the time period. Okay, so it is simply the evolution of the part. Okay, so the evolution of the harmonic oscillator to make it is one cycle. Clear? So now let's consider the evolution of the harmonic oscillator for a larger time. Okay, like this thing. Let's make a change in omega this way. Okay, so if what adiabaticness means, adiabaticity means you evolve system slowly. How slowly is that? Such that the time scale on which you are expecting a change, okay, so it is larger than the intrinsic time scale. Here the intrinsic time scale is actually the time period of the oscillator. Clear? So let's plot it. I mean schematically. Clear? So let me consider this as some time t. Okay, and you are having this as omega t. Let's consider. Let's say t equal to 0. I am having some omega. Let's say omega t. So it varies like this thing slowly, like this thing. Let's assume. So this is a slow variation of omega. Clear? Okay. So let me consider the change over a time. So this is the some time tau. Okay. So you can observe a change at this very time. Clear? So if you consider, let's say, the time period. So this is the amount of time period over which there is an oscillation. Clear? So let me consider this as the time period 2 pi by omega p. Okay. So now you see I have changed omega slowly. Clear? Okay. So I am changing omega slowly over a period of t. Clear? Over a period of tau. Clear? Got it? Okay. So if this tau is very large than this t, that means only at this time scale there is an appreciable change. Clear? You figure out an appreciable change in the evolution. Then I can say it's an adiabatic evolution. Got it? Samajhan? So adiabatic evolution means you require at least 2 time scales. Okay? An intrinsic time scale on which a system evolves and a time scale on which there exists changes. The changes are appreciable. Okay, so this is a time scale at which the change is appreciable. Clear? Now, if I take this tau, let's say as small as t. Clear? Let me assume this tau, this small time scale, appreciable. Okay, so of the same order. Clear? As this very time period of oscillation. Clear? So can I figure out the change? No, there is no appreciable change. Clear? So you can see then evolution is kind of smoothness. So you can think, okay, you can consider this kind of situation as well. Think of a cylinder with a piston, is it? So you move piston very slowly such that the equilibrium at each point is maintained. So that you call as an adiabatic process. So it is the same kind of thing. Huh? Okay, so only the appreciable change what you observe when the piston moves to a finite length. Clear? Not so the intrinsic length scale is there, those infinitesimal steps on which you are moving the piston. Okay, and the scale at which you are looking at the appreciable change in the system is at the finite length. Okay, the length up to which you are shifting your piston. Clear? Got it? Okay. Okay, so what does this imply? So if I am having this adiabatic, everybody got the adiabaticness? Okay, so if I am having the adiabaticity, or there is an adiabatic evolution, what exactly it means? What it implies? Okay, does there exist any conserved quantity, or at least does there exist any invariant quantity? Okay, or how I can describe the motion, an adiabatic motion. Clear? Okay, so for that matter, let's consider this kind of ratio for this harmonic oscillator. Let me take this h of t by omega t. Clear? Got it? Let me consider this kind of ratio. Okay, and let's check. Okay, let me call this as I. Okay, so what is our question? So I am saying I am having adiabatic motion. Clear? The system evolves adiabatically. What are its implications? Does there exist any conserved quantity or does there exist any invariant quantity? Okay, got it? Okay, so suppose if you are having the adiabatic thermodynamic process, what are its implications? What are the conserved quantities? Suppose what an adiabatic process means in thermodynamics. So think over it. Okay? So I will not answer it. So you should have done it at earlier classes. Okay. So so that whatsoever remains conserved there, that's an implication of that adiabaticness. Clear? Okay. So let me consider this kind of ratio. Okay, so differentiate it. Okay, so let's differentiate it. Okay. So what is the differentiation? So there will be 1 by omega square t. Then differentiation करते हैं. Next set question to rule ना. करते हैं differentiation. अगर ना तो differentiation तो करंट के. तक हमने में question rule of differentiation. when is it? Huh? You mean this way? You mean this? Then?
Divided by.
Is this the case? So this is simply the question. So now what is h dot? That we have figured out. So what was that? So just calculate. So
Divided by 2.
omega square of t. Yes, we have calculated. So you are having omega of t. What is h dot of t?
M omega dot
M
x square.
omega dot
X square.
x square. Good. Minus what is h? So it's p square by 2m. So that's half of m omega square t x square and omega dot. Clear? So you can take omega dot out. Here is omega dot, and omega dot is there. So you can write this as di by dt. So how much is that? So omega dot t by omega square t. So what remains here? So you are having simply look here. So it is m omega square x square and minus half of this thing. So it's simply half of m omega square x square then minus t square by. So what is that equal to? Omega dot t by omega square t. So it is, let me write this as some, since this is a potential energy, so let's write it as V of t minus some kinetic energy. Okay, so V of t is this thing and V of t is this. Clear? Okay, so I have not assumed any approximation yet. Clear? So this is some exact result. I have considered this quantity and we will interpret this quantity what exactly it means. Okay. So now let's look at this thing. Suppose I am having an adiabatic evolution. So that means I am adiabatically varying omega. Okay. So it means omega is changing slowly. So what about this very quantity? When omega is changing slowly, its derivative will change slowly. So it means this is a very small quantity, omega dot by omega square. Clear? So it is very small quantity. Now what about this thing? So that means this will change slowly over a given period of time. Okay. So what about this very quantity? How fast it will vary? Okay, so we need to consider it. So can anybody guess how fast it will change? Anybody? Okay. So let's check it. Suppose if you are having harmonic motion, since we are considering the harmonic motion, clear? So how we assign the coordinate? So x of t is always a of, let's say, sine of omega t. Clear? So this describes the harmonic motion. What will be p of t then? A m omega cos of omega t. Simply differentiation. Just substitute it there in this very case. Okay. So I will write this thing. Okay. So let's write this v of t minus p of t. So it will be okay. So I will forget this a. Put this approximately. Okay. A is simply the amplitude. So how much is that? Anybody? Okay. So it is x square. So m omega is there as well. So what it will be? M omega square t then cos
Omega
of
t.
twice omega t. So with a negative sign because we will be having cos square here. Clear? Is it true? Okay. So now it is very fast, because it moves at which frequency? 2 times. So that means this oscillates very fast. This very term. Got it? This is a slower term and this is a very fast term. Okay? But there is omega square t because omega is varying slowly. So we'll see actually the net effect of this objective. It's if I am having adiabatic evolution, its change is very very small. Clear? Got it? Okay, so let's check it. Let's calculate this for. Okay, so let's calculate its variation. So it's okay. If it okay, although this is very small if omega changes slowly, but it's not a priori clear because it changes at a frequency of 2 omega. It's an oscillating term. Clear? So it's not a priori whether this term will go to 0 or not. Clear? So let's calculate the value of this I over a time period evolution, time period of the harmonic oscillator. Okay, what I mean by that? So let me calculate this thing. T is the time period of the evolution. Okay, I of t. So let's calculate this change. If this change on a time, since t is very less than tau, clear? So tau is our time evolution, clear? On which there is an appreciable change. I am considering this time. Okay, so the time period of the oscillator is smaller than this tau, clear? Got it? That means the adiabatic approximation in terms of the time scales. So what I am looking at, so what this change is. Okay, so if this change turns out to be 0, that means on the time scales of this order, so this IT is constant. Clear? So that, okay, so if this turns out to be 0, this difference, that means at, okay, I at t plus capital T is same as I t. Clear? So that means over an evolution, when I am making an adiabatic evolution or if I am changing frequency of the oscillator slowly, that this I remains constant. Clear? So if it remains constant, it means it is an invariant quantity. Got it? Okay, so let's calculate it. So how I write this difference? So you put this difference as t plus tau di by dt. Let me write t prime. Clear? So this is simply the difference in terms of the integration. Okay, so let's put the value of this differentiation. So it is t plus tau, and this is capital T, not tau. So let me write this dt prime. So then you are having this omega dot t prime by omega square t prime. Okay, then this v of t prime minus k of t prime. Clear? Okay, so now what we are doing? So we are changing slowly this omega. So in this very interval, so if you look at that very picture, so in this very interval here, so omega does not change appreciably. Clear? So it's a very slow variation. So that means in this very domain, I can pull it out. Clear? So if omega changes, okay, so in this very domain, okay, if omega changes slowly, okay, so then this is very small, omega dot by omega square is does not change appreciably. Yeah? Over a time period. Clear? So in this very time period, it does not change. It remains approximately constant. You can take it out. Okay. So what it means? So you are having this I t plus t minus I of t. Okay. So this is simply omega dot by omega square t. So t plus tau, then you are having dt prime, you are having vt prime minus kt prime. Clear? So if you see this is, if I divide this by 1 by capital T multiplied by capital T, it will be simply the average of this potential energy minus average of the kinetic energy. Clear? Now if you are having a harmonic oscillator, let's forget about omega is the frequency dependent. So the average of potential energy is always same as what? average of kinetic energy. In that very case, this will go to 0. Got it? So the two effects will cancel out. Now since omega is changing here, but the change in omega is not appreciable. Huh? So it is essentially actually constant for this time period. Clear? Got it? So that means the average value here should be same as average value here. The average value of potential energy should be same as what? Average value of kinetic energy. This is only possible if the omega is changing slowly. Yeah? Got it? Okay, and how much slow is that? So there is no appreciable change within this time period. Got it? So in that case, this will be approximately equal to 0. Got it? So what we got then? So I of t plus this capital T is same as I of t. So that means this I is actually the invariant of motion. Huh? Clear? So in other words, what we have, so what is I of t? So I is simply this h by omega. I wrote it as like this thing, or you can say, let's say for a harmonic oscillator, it is since h is the Hamiltonian, it gives you the energy. Clear? So energy by this frequency, this is an invariant quantity for the harmonic oscillator. Okay? So these invariant quantities we call as the adiabatic invariants. So this ratio forms an adiabatic invariant. So it is known as adiabatic invariant. Okay? So the value of an adiabatic invariant for the harmonic oscillator is what? E by omega. Okay, so you will see its consequence in a moment. Okay. So let's look at harmonic oscillator again in the phase space. Huh? So in phase space, okay, so you are having this. This is the equation of harmonic oscillator. Okay, is equal to E. So if you are having energy is conserved, we consider energy conserved. Clear? Okay, so how it describes an ellipse in phase space. You know that? So if let's draw the phase space. So you are having this as x and this as p. So it is simply as an ellipse. So let's say this is the major axis and this is the minor axis. So you can write it like this thing: x square by a square plus p square by b square is equal to 1. So where a is equal to root of 2m by e probably. So what is it? 2e by m omega square. Okay, so it is 2e by m omega square and b is equal to root of twice me. Okay, so you divide it here and omega square you put in the denominator. So you will get this kind of thing. Clear? So that means for every energy, so you will be having what? A circle. So if you increase the energy, you will get what? You get another ellipse. Huh? So that means the evolution of the harmonic oscillator in phase space is simply the evolution of the ellipses. Huh? Okay, with larger areas. Huh? Clear? So you will be getting, you will be getting another ellipse. Okay, so it will go as, so each this trajectory is having fixed energy. Clear? Since if I am moving adiabatically, so this ratio will be what? Constant. Clear? So this is actually, so you will be having for this trajectory e by omega constant here. Got it? So if you move adiabatically. Clear? Now let's look at what is the area of this ellipse. How I can write the area of the ellipse? Anybody? So area of ellipse is how much? So that is pi times AB. It is simply the area of the circle. If A is equal to B, it is pi square. Clear? So now what is A? So if you see, so A is root of 2e by m omega square. B is that. So it will be simply 2 pi e by omega. Got it? So that means area under the ellipse is described by this adiabatic invariant. Okay, e by omega is the adiabatic invariant quantity. Clear? Now I can write the area of the ellipse under this. So area under this ellipse in this fashion, like this way, as a closed line integral p dx. Can I write it? So this is area. Is that true? So how much is that equal to? So now by this very definition, how much is that? E by omega. Clear? So in other words, this integral remains invariant. Okay, since this is an adiabatic invariant, this quantity is an adiabatic, this remains invariant under the adiabatic evolution. Clear? In other words, the value of this integral is what? Invariant under adiabatic evolution. We call these integrals as adiabatic integrals. Okay? Or adiabatic invariants. Okay? So therefore I can have an adiabatic invariant in terms of the area. Okay, like this. So it is simply integral p dx. Okay, 1 by 2. Okay, and for the this harmonic oscillator, this adiabatic integral is simply equal to e by omega. For different systems, the value ratio will be different. Okay, got it? Okay, so this is all the adiabatic. Adiabatic evolution in classical mechanics. Now let's look at what are its implications in quantum mechanics. Got it? Okay. So now look here. There is one important point. When you move adiabatically, the state of the system is defined by the same variables. Okay. Suppose if you are moving piston from one place to in the infinitesimal amount such that thermal equilibrium is maintained. So it is always described by the same set of variables. Okay, what you started with. Okay. So similarly, how this curve is defined? If you see, it is defined by e by omega ratio. So this curve will be always defined by e by omega ratio by the same set of variables. Got it? Samajh? Okay. So that means the state of the system does not change. Any questions till now? Okay, so let's look what are its implications in quantum mechanics. Okay, so let's look. Yes, in quantum. Let's look at this harmonic oscillator again. What is the energy of the harmonic oscillator? Yes, any question, beta? So why you are making noise? Okay. So let's look at the harmonic oscillator. So what is our Hamiltonian? So h cross omega sum a dagger a plus half. Clear? So now what is energy? So energy is simply h cross omega, so n plus half, where n is the quantum number. N is quantum number that specifies the levels of the harmonic oscillator. Okay, so it goes from 0, 1, so on. Clear? So now let's look at, okay, so what is our adiabatic? Okay, so let's look at this very ratio, e by omega. So how much is that? So it is simply h cross n plus. Clear? So what does it mean? Suppose if I am evolving adiabatically, clear? So what it implies? So the quantum number is fixed. Quantum number of the state does not change. When I am moving adiabatically, that means you start with some wave function of the harmonic oscillator. Let's say here harmonic oscillator, and you evolve to a new state. Usually, what we should get? A new state, clear? Defined by new quantum numbers, clear? But when we are evolving adiabatically, what is happening? Quantum number remains same. That means the adiabatic evolution does not change your quantum number. Okay? So the state which has evolved adiabatically, so it has the same set of quantum numbers. You describe it by the same set of these variables. Clear? So okay, so this is from, okay, so let's look from this semi-classical approximation. So we are having another approximation, what we call the semi-classical approximation. Okay. So we are having this integral. This is known as Bohr for any arbitrary. Since I have considered here only the harmonic oscillator. Clear? Got it? Yes. So now let me consider a potential okay, which has turning points. Let's say you are having the potential which has turning points at point A, at xa and x equal to b. Clear? So you know these things? Huh? Turning point means where energy is equal to the potential. Okay? So here the energy, if the particle is here at this very point, so this is the height of the potential here. So E minus V is equal to 0 at these points. Clear? So you can see this is a turning point. Okay? So, okay, so we are having this very condition, what we call it the Bohr-Sommerfeld quantization condition. Okay? So it says if you are having this kind of integral p dx, clear? And p is given by, okay, so from Schrodinger equation, p is simply equal to twice m e minus v. So you can calculate it simply from the potential. Here the potential is varying actually slowly. Okay, so it turns out to be like this thing. 2 pi h cross probably n plus half again. Yes, it is n plus half. Okay, so this is for any arbitrary potential. So you have to solve this kind of integral. What you will get? You will get the value of the energy. So you can solve this integral for any bound state problem. So let's put P is equal to that and potential is given. Clear? Okay, and solve this integral and equate it on this very side. You will get the energy corresponding to a given potential because V will be the function of coordinate. Clear? Got it? Okay, so if you don't know this kind of condition, but let's assume this condition is there. So this is valid for any arbitrary potential. Clear? For the bound states. We are considering here only the bound states. So now look here, this integral we have shown what it is. It is an adiabatic invariant. Clear? So this was actually for a specific problem, while we have shown the adiabatic evolution implies the quantum number remains same. That means state of system remains same. Okay? Or the state of system is specified with the same set of quantum numbers. So if this is adiabatic invariant, which we have shown just now, so it means it only depends on the quantum number. Clear? So it means if you are having an adiabatic evolution, the quantum number remains same. Okay? Got it? The time evolved state has the same set of quantum numbers. That means we can describe it by the same set of quantum numbers what state you started with. Clear? Okay. So let's look at from the time dependent perturbation. Okay, any question here? Okay. So it is actually the content of what we usually call as the adiabatic theorem. Huh? But I am giving you, it is physical, physically, we are putting an intuition, huh? How it looks like, then we can prove it mathematically. Yeah? Okay. So now let's look at the time dependent perturbation, what that says. Okay, so you are having the probability. Let's say Pi goes to n at time t. You start with some state I and go to n. So how much is that? So it is Cn1. At first order, let's calculate. So it is like this thing. Clear? Yes? Any problem? Okay, so it is something minus I by h cross. So let's evaluate for some time t dt prime e raised for I omega ni t. Then you are having v ni t prime. Clear? So this is the mod square. Got it? Now if I am saying I am having, let's say, if my potential changes slowly, because the time dependence comes from where? Potential term, huh? In the harmonic oscillator, I assume the time dependence enters from the omega, clear? And I am changing frequency slowly. Now here in time, this very case, so the potential, this time dependence comes from this very potential, okay? The perturbation. Now if this is, if this varies slowly in time, clear? If this varies adiabatically in time for a given period of time, so this is essentially constant term, clear? So much of this will not vary appreciably. You can take it out, okay? So you can, or you can think if the perturbation is constant in time. Let's assume perturbation is constant for certain interval in which we are interested in. Okay, so this is constant, it will come out. So you will be having simply V and I mod square. Okay. Now then only remains what? This integral. Integral of this thing, if you see, it is simply e raised power I omega ni t minus 1 divided by mod square omega ni. So I should put it over a time period, or some time t. So this t is less than the total time of the evolution. Clear? Okay, so now let's look at this very formula. So it is simply the integral of this thing, exponent e raised power I omega t. So it is its integration, and I will, because there is a mod, I will go. Okay, since this is a constant term, so let's assume the discrete states first. Okay, so suppose if you are having this I, and let's say this is n. N can be anything. Any of the states can be n whatsoever. Okay. So since perturbation is constant, it is fixed. This very term is fixed. Now for any appreciable jump from this very state to where the energy gap is very large to larger states. Clear? Let's say if the gap between the two states is very large, what will happen? So this is very large. What is omega ni? So it is simply the difference between the energies. Clear? So this is very large term. That means this quantity is suppressed. Okay, even I am applying the weak perturbation, a time dependent perturbation. Okay, any appreciable jump from this state to any other states is highly suppressed. There is very least probability. Clear? So what does that mean? So that means this is very small quantity. So what does that mean? So the particle remains for all times in this ground state, in that state I. Clear? So that means if you evolve your system slowly, clear? So still, okay, even if you are having a time dependence, it will always remain in that very state under adiabatic approximation. Clear? Samajh? Or the state, what the new state, what will be formed, it will be defined by the same set of quantum numbers. Got it? So this is very important rule. Okay? So now let's do the calculation. So if you have any question? Okay. Yes. Any question? So let's consider an instantaneous eigenstate of our Hamiltonian. So let me consider n of t an instantaneous eigenstate of h of t. Okay, so that means at a particular time, this n of t is the eigenstate of our Hamiltonian, like this. So this is a time dependent term, this h. So let me write it. Okay, so it is simply equal to, let's write E n of t, n of t. Clear? So, but you should know this n of t is not a solution in general for the time dependent Schrodinger equation. Clear? Got it? So this n of t, okay, I should write here. So n of t is not a solution, okay, in general of time dependent Schrodinger equation. So that means, so you are having IH cross partial by partial t n of t, okay, is not equal to this h of t. Okay, so let's try to solve the Schrodinger equation, time dependent Schrodinger equation. Clear? Got it?
Yes, sir.
So let's try to solve it. Okay, so we are having, let's take the psi of t as the solution of time dependent Schrodinger equation. So what is that? I I H cross partial by partial t, this psi of t, okay, it is equal to H of t psi. Okay, so if we don't have any kind of time dependence at all, okay, in this way, if they are simply the stationary eigenstates, okay, if there is no time dependence at all. Now tell me how I can solve that Schrodinger equation. How this psi of t look like? So if you know, okay, anybody? Suppose if you are having simply this h, n is equal to e n n, clear? So how psi of t I can construct it? This psi of xt, how I can construct it? So it will be simply sum of all these sum of all these solutions, clear? So I will write one of the solutions. Let me write, it will be some Cn e raised for minus I e n t by h cross, then some psi n. Okay? Where psi n is what? So let's write the psi n. So psi n is actually the eigenstate. So psi n means simply, okay, or you can write it like this thing, psi of t. So you can simply write it as Cn e raised for minus I e n t by h cross and n. Clear? Got it? So in this very notation. Okay, so what you have done? You have simply written this psi of t as some constant Cn which needs to be figured out, and an exponential factor which represents the phase. Okay, so if you substitute this in that time dependent Schrodinger equation, what you will get? So you will get an equation like this thing, Hn is equal to En. Clear? You know that? So it is simply the separation of variables in terms of the time, a time dependent part and the time independent part. Clear? So these will form the stationary states. Now I need to construct that psi of t. Got it? So what here is, so the energy is actually time dependent. Clear? So in an analogous fashion, what I will do, I will construct this psi of t this way. So I will write this psi of t like some constant Cn of t. Okay? So sure? Because now the coefficients will be time dependent. Okay, and some e raised for minus I by h cross, because now the energy is varying over some time. Clear? Let's say the time of evolution is this t. So you will put some e t dt prime. Clear? So okay, so let's say e is constant. So you can take it out of the integral, 0 to t, dt is simply t. Clear? So it will be minus I by h plus e. That. Got it? Yes. Then I will put this factor n of t. Okay? So what is unknown to us? Cn. So I need to figure out what this Cn is. Let's substitute this equation here and try to figure out what this Cn is. Everybody followed it, what I am trying to do? Okay, so what I am trying to do, I am trying to construct a time dependent wave function. Clear? Okay? So we are trying to solve this kind of equation for the adiabatic evolution. Got it? So for the adiabatic evolution, now look here, if you look at this very equation, it says this n of t is actually the eigenstate, even it evolves. It is an instantaneous eigenstate. Eh? So at each time, n is an eigenstate. Got it? So let's say if you take t tends from 0 to some time, clear? So this n will be always an eigenstate. So that's why we have constructed the instantaneous equation in this fashion. Huh? Got it? Okay. So this is true only for, so if I am having the adiabatic evolution. Got it? Okay. So let's try to construct these Cn's. So substitute it in the above equation. Okay, so you are having, let's take this LHS. So it's I H cross partial by partial t psi of t. Okay, so how much is that? So psi of t is that Cn. So it will be, okay, so let me write it, partial by partial t. Okay, this Cn of t is for minus I by h cross 0 to t dt prime e of t prime. Then you are having this n of t. Okay, there is a time dependence in n. So it is I H cross. So what it will be? C dot n of t and e raised power minus I by h cross 0 to t dt prime e of t prime n of t. Okay. Then you are having okay Cn of t. So this minus I by h cross will come down. When you differentiate this thing, it will be simply e of t. Clear? So then you are having exponential back 0 to t dt prime e of t prime. Then you are having n of t. Then you are having 1/3 term Cn of t e raised power minus I by h cross 0 to t dt prime e of t prime. Then the differentiation of this thing. Let's call that differentiation of n dot t. Got it? So this is equal to RHS. So this is equal to RHS. Okay, so let me write the RHS part. So shall I write it? Okay, the first step we can erase. So what is our RHS? H of t psi of t. Clear? So what is that equal to? H of t. So it is H of t Cn of t e raised power minus I by h cross 0 to t dt prime e of t prime and n of t. Clear? Now these are numbers, actually act on that. So what you get? So you'll get simply ENT. So En of t Cn of t e raised power minus I by h cross 0 to t dt prime e of t prime n of t. Clear? Now let's look at this very term, this second term. So you are having IH cross is multiplying, is it? So IH cross and this IH cross is gone. What remains there? CNT, ET and this thing. So you are having this as same. Clear? So this term will cancel out with this term. So what remains there? Everybody followed it?
Yes.
Okay, good. So what remains? So you are having, okay, so IH cross is multiplying both the terms. The sum of these two terms is equal to 0 because there is nothing on right hand side. Okay, so it means this C dot n of t. Then you are having this exponential. Exponential is on both terms, so that I will remove. So what you are having simply n of t, that's equal to minus C n of t. Okay, then you are having this n dot of. So you are having a differential equation now. You have to solve a differential equation. Is this a differential equation? Okay. So now what I will do, okay, so let me multiply this on left hand side. Let's operate this equation by n of t. I want to free it from this n of t here. Okay, otherwise it's a vector equation. If you see, you are having a vector on this side and vector on this side. It's a vector equation. Clear? Huh? So I have to solve a vector equation. Okay. So okay, so remember this equation. There is a fault in this equation. Okay, the way we are going to solve it, there is a fault. Okay, but I will tell you later on. Okay, so let's call this equation. Call this equation first. Okay. So let's multiply it. So it will be something C dot n of t. Okay, then you are having this n of t. So that is minus Cn of t and n of t n dot of t. Clear? So now n of t it is 1. So it implies simply C dot n of t. Okay, so that's equal to minus Cn. Okay, n of t n dot of. Okay, so it's let's call it as a differential equation in C. Clear? So you are having Cn on this side. So it's simply, let's say this is f of t. Clear? So it is something x dot is equal to minus x f of t. So what is the solution? So the solution to this very problem is Cn of t is equal to Cn of 0. Okay. So exponential of minus integral, because there is a minus sign. So minus integral, okay, some 0 to t, let's say, dt prime, okay, n of t prime, okay, n dot of. Got it? We have figured out what? What we have figured out?
Cn of t.
Cn of t. So we have written this thing. Now there is a subtlety in this very equation. So we have solved for one Cn of t. Okay, so let me point it out and then we'll do the. So there, the calculation what we have done from equation first, it's an approximate calculation. It's not a complete calculation because if you see the n of t, so it's an eigenbasis. Clear? Since we have started with n as the eigenstate of some Hamiltonian h. Clear? So that means there are many states in that very eigenset. Got it? Okay, good. Now if you look at this very equation, so this is actually a vector equation. Clear? So I need to choose suitably a basis to solve this very equation. I have chosen actually only one of the vectors in that basis, which overlaps with this thing, gives me identity. Clear? It's not necessary that this will be same as this thing, or it is not necessary that this vector or this vector will be actually orthogonal to the other vectors in that very basis. Got it? Samajh aawa?
Yes, sir.
So in that case, this the solution is approximate only. It's not an exact solution. Okay. So okay, so let's look at this very quantity, this n of t. So you are having this n of t, n dot of t. Let's look at this very quantity. This kind of overlap. Okay, so let's check it whether it's a real quantity or an imaginary quantity, or it is a whether it's a purely real or purely imaginary or a complex number. Let's check it. So can I write this? Okay, so let me write it in this coordinate space. When you are having bra n, so it means you are having psi n star. Okay, so when you are having this thing, so it is simply d by dt of psi n. Clear? And there is an integration over x. Okay, so can I write it in this fashion? Integration over x. So it will be simply d by dt of, okay, psi n star, psi n minus d psi n star by dt psi n. Can I write it? It is simply I have written the things. You just differentiate it, you will get back. Okay. So what about this very term? So this is 0 because psi it gives you the property. Clear? It's a constant. Okay. So it means what you have got simply minus dx, okay, d psi n star by dt psi. So let's put it in the cat notation back. So it is minus. So it will be simply n dot. Now n dot is on this side. Okay. And n is on this side. N of t. Clear? Got it? Okay. Can I write it this way? Since if I interchange the two, I have to apply the star. Okay, simply the complex conjugation. So you put a complex conjugation on this thing, you will get back. Clear? Now is this the same thing? That? So when you are having a number z equal to minus z star, what does it mean? It has to be purely imaginary. Okay? Because we can, okay, so it is a plus ib and it is minus a minus ib. So that means a and a cancels. So you are having only b is there. Okay? So got it? So it has to be purely imaginary. So which implies n of t, okay, n dot of t is purely imaginary. Okay? Got it? So when this is purely imaginary, what I will do, I will multiply it by I. What that will become? Real. Clear? So let's multiply it by I. Okay, if I multiply it by I, so I will. Okay. So let me define certain quantities first, then maybe you can appreciate it. Okay, so let me define this. So, okay, so let me write it as psi of t, like this thing. So what is Cnt? So it is Cn of 0, e raised power. Okay, so I will put as a minus I. Okay. Okay, since there is a minus sign, I will put an I square. So it is I integral of what it is? dt prime 0 to t, and you are having I here, so n of t, okay, n dot of t. Can I write it? Okay, so now this is a real quantity, eh? Okay, I is here. Then you are having this exponential e raised to power minus I by h cross 0 to t dt prime e of t prime, and then you are having your this n of t. So let me write now a quantity theta of t is equal to 0 to t, okay, 1 by h cross 0 to t dt prime. So we, since this is a phase, these are all phase factors, so this is a phase which depends on energy, clear? So we call this this phase factor as a dynamical phase, that I am writing in terms of theta. So this is the dynamical phase. So that means if you are evolving adiabatically in a given, if you are evolving adiabatically a given state vector, so that will be accompanied by a dynamical phase change, clear? So only the phase change matters, and there will be another phase, what we call the periphase, okay? So our geometrical phase I will tell you. Okay, so I'll write this v of t, define it as like this, n of t with the sign I, n dot of t, okay? So let's define this name such that I am having, so let me write this gamma of t is defined at therefore integral 0 to t dt prime nu of t prime. Clear? So this we call as a geometrical phase or the periphase. So it is related to the geometry of, so this I am going to teach you in detail, this phase. So this will give the idea of the monopole existence in quantum mechanics. Okay, so what we are getting here, therefore this psi of t, so it is equal to Cn of 0, so e raised for I gamma of t, e raised for I theta of t minus, okay, and then you are having n of t. So that means if there is an adiabatic evolution of a system, okay, so let me put it as an approximate instead of the exactness. Let's put it as approximately. Clear? Because I have said and the equation 1, so if I have to solve that, I have to consider the complete basis. Okay, got it? Any question? Huh? Okay, so psi of t I have put, because this is Cn of t. For Cn of t I have written this. So the equation we have solved for Cn of t, that is only for one vector. Clear? You got my point? Okay, so I have to solve that very equation for all the bases, because that's a vector equation. Okay, so that you have to solve for each vector, and it is not necessary all those vectors will be orthogonal to each other, okay, at a given instant of time. Okay, you have to orthogonalize that as well. That's why I have put it as approximately here. Okay, so the same is here. So this we call as the geometrical phase or the periphase. This is also known as Pancharatnam. Pancharatnam was an Indian physicist who actually described this kind of phase before Berry. Michael Berry was actually, he proposed it later on. Okay. Okay, so there are many phases, they are all related. I mean, there is what we call the Aharonov-Bohm phase or Berry phase, or they are the one and the same thing. Just the I mean the implementation is there. How you constructed them. If you look from the geometrical perspective, then it is simply the Berry phase. Okay, here we call it as simply the geometric phase. Okay, although they are one and the same thing. This has actually the geometrical construction. Suppose, okay, so let me tell you this way. Suppose if you are having some surface, some smooth surface, let's think of a sphere. So if you move a vector on the surface of the sphere to another point, okay, so that vector will have a phase. Although the set of quantum numbers initially will be the same as the at the final point, but only the state vector will have a phase associated with it. Okay, and that is a geometric phase. Usually in quantum mechanics, we don't observe the phases, is it? But these phases are something different than those kind of phases. Okay, so this will go in detail, and this leads to the construction of the monopoles, magnetic monopoles in quantum mechanics. Okay.